distribution functions, characteristics functions, central limit theorem, entropy probability, entropy maximization, and all that. So, going into that, we must look into the aspects of basic statistical mechanics. And we have read in thermodynamics that the thermodynamics deals with certain parameters, that is temperature, pressure, volume, entropy, enthalpy, internal energy, heat. Those are treated as your basic parameters or thermodynamic variables. But in order to explain statistical mechanics, we have to know the some properties, and it basically deals with the probability aspect. So certain terminology, to read the probability, we must know certain terminologies. What are those terminologies? First one is a trial. What is a trial? It is an experiment performed and repeated under identical conditions. That means I have a coin, I will throw it, and by throwing, there is two possibilities. One is head, the other one is tail. So I will tell how many events I have performed in this trial process. In this case, if we say head will occur every time, then that is an exclusive event. If we say head and tail have equally likely possible, then they are called equally likely events. If we say head is only required for us to reach to bat something in a cricket match or anywhere, we tell it those are favorable events. If the head comes, or in a dice 6 comes various times as per our requirement, we say those are favorable events. If an event does not expected but it randomly enters into our trial process or event process, this is called your random event. Again, those events may be dependent. So if dependent, they are called dependable events. Otherwise, if it does not depend, they are called independent events. So these are the basic terminologies. Then we have to know probability. We have read all probability in our +2 classes. So what is probability of an event? Probability of an event is the ratio of number of ways leads to the event, if leads to the event of interest, to the total equally number of like events. Suppose an event occurs in m ways and fails to occur in n ways. That means we have m number of events occurring, and the failure of the event is n times. So what is total number of events? Total number of events is m plus n. M is number of successful events, number of meaningful events or interested events. We need here m times. We does not need tail. Let it tail occurs in my event n times. So what it indicates? Total number of events is m plus n. And the probability becomes normal probability is m is our favorable event divided by total number of events, that is m plus n. M is favorable event, n is our undesired event. M plus n may be treated as big N. So this is P divided by m plus n. And if it in your choice, it has been written this line, PB is n of n minus na by n, that is 1 of PA, probability of occurrence of event A and probability of occurrence of event B. And what is its percentage is 100%. PA plus PB is 1, which means sum of probabilities of an event occurring, not occurring is unit. Hence, we decide what are the conditions. If this is the probability case, what are the conditions? Let us discuss with one example. Suppose we have head and we have tail. So what are the probabilities? The probability of head is half and the probability of tail is half, such that half plus half becomes equal to 1. And now if you consider what is the condition, then you can say probability of B or A can be written as probability of A intersection B divided by probability of B. Similarly, if probability of B with respect to A, then probability of B intersection of A divided by probability of A. So what does it indicate? It indicates to obtain a probability distribution, we have either some discrete distribution as per our desired requirement, or we have some continuous requirement. And the probability cannot be greater than 1. Probability of any event is always less than 1. Then if probability is 1, what happens? Then it is a certain event that will definitely occur, that is a certain event. Then there are general rules of probability. You have read, one is your positivity. Positivity. PA is probability of an event A. Then PA is equal to lies between 0 to 1. If PA is 0, this is likelihood event. If PA is 0, this is likelihood event happening, and PA is 1, then event A is certain event. Then additivity, if A is and event B are independent or disconnected, then P probability of A intersection B is probability of A probability of B subject to the condition A intersection B is equal to phi, and that satisfies the relation f of x plus y is fx plus fy. What is multiplication law? Probability of AB is simply probability of A multiplied by probability of B. That is multiplication of law. What is normalization? That is, if you perform an experiment and the outcome must be sample points in the sample space S, then PS is equal to 1. And you know, the normal way of expressing the probability can be written, normal way of representing probability, the sum over I, Pi must be equal to 1. The summation sign is only valid for discrete distributions. Then we can interpret in, if we have subjective interpretation, then what is outcome of likelihood event of head? I have told you probability of finding head is half and probability of finding tail is half if you throw a coin, and because it has two faces. So what is frequency of occurrence of that event? Now if you find probability of head, that is equal to number of times the head coming divided by total number of events. Probability of tail is the number of times the tail coming divided by n. So there's some example is given. If you have a dice, it has 6 faces. If you find probability of 3 or 4, then you can find probability of 3 is 1 by 6 times and probability of 4 is 1 by 6 times, and the total outcome is 1 by 3 as per your additivity property. Then we come across the permutations. We have read the permutation and combinations in our +2 stage. So while considering the permutation aspect or combination aspect, at that time we say, how can we explain 15 number of say devices are here? How can we represent in different cells, different compartments? In that case, or we have a macro state having large number of microstates. So how we can explain all the microstates in that macro state? Let us have the example. Suppose there are 3 persons. 3 persons are A, B and C. They are to be seated in 2 chairs. 2 chairs are available, but there are 3 persons. So what are the possibilities? The possibility is either A, B, C, that is A, B, or B, A, or C, A, or A, C, or B, C, or C, B. So by 6 ways, they can accommodate the two chairs. If we consider the permutation of n objects in this manner, and objects are taken small n times, then what is the probable permutation? Permutation is n written as, if we have n number of objects having small n number taken at a time, then the permutation is n factorial divided by n minus n factorial, which can be represented by this one. Then the binomial coefficient expansion, we know from the binomial expansion theorem, x plus y to the power n is n c0 x to the power n nc0 x to the power n nc1. This one we know binomial theorem. When you apply in this binomial theorem, we can also express the probability of the equation. But we have, in this case, it depends on the variables. Then if variables are random, then we can have their probability distribution. Suppose x is a random variable, then its probability distribution can be written as f of x. But if we have two dice, let us have an example how the random variables are occurring. If we have two dice, that means dice has 6 faces, 1, 2, 3, 4, and you will find up to 6 faces. So what are the combinations possible? You can find in the dice, the first combination, they must have 1, 1. In second case, they must have 1, 2 or 2, 1. Third combination, 1, 3, 3, 1, 2, 2. Fourth combination is 1, 4, 4, 1, 2, 3, 3, 2. In this manner, we have the combinations of many types that is possible. Many type combinations are possible. So to represent these combinations, these 12 faces, we have represented the number of combinations giving rise to the sum 2, 3 up to 12. So out of 36, these are 36 ways we can combine them. Hence, the probability of getting, what is the probability of getting 2, 3, and 4 in this combination? The probability is 1 by 36, 1 by 18, 1 by 12, 1 by 9, 5 by 36, and this is the probability. So in general, if a variable x takes values x1, x2, x3, xn, then the probabilities of finding x1 is fx1, probability of finding fx2, fx3 up to fxn. Then we can write x is equal to xi if you generalize it, then f of x is called probability distribution. Remember, we have probability of x1 is fx1, probability of x2 is fx2, probability of x3 is fx3, then probability of fxn is fxn. Then we can write this is probability distribution of x. In physics, we use probability theory to predict the behavior of a system in statistical mechanics. And so probability behavior, what it indicates, it elaborates the vital link between behavior of atoms and molecules. In order to explain a large number of atoms and molecules and correlate the behavior among them, we have discussed the probability distribution function. It will help us for details we will tell you in Unity 2. Then we will explain how a system is described in equilibrium condition. Next is you are in 1.3, in equilibrium condition, how a system defined. We are finding the thermodynamic description. I have told you thermodynamic description deals with the macroscopic objects, labels. And statistical mechanics, microscopic molecules, very small molecules, that is kept in number of cells. Number of molecules, how many number of molecules can be identified in how many cells. So we will keep equilibrium among all these cells with respect to their energy, their volume, number of particles, chemical potential. If they are treated, they are either equal or they are in combination, or then we say these are the equilibrium systems, or these systems are in equilibrium. Another point, we have to read the phase space. You have read in classical mechanics, to describe a system, we need momentum in Lagrangian formulation and Hamiltonian formulation. You have described it in terms of position and momentum. This comes from the principle, uncertainty principle, that is delta P into delta X into H, which is equal to delta E into delta T. So in a coordinates axis, we can represent, if x, y, z are three coordinate axes, corresponding momentum are px, py, pz. And what is phase point? Now the space defined by this method is called phase space, and the point is called phase point. You have read this one. This one is your phase coordinate axis, and the point P represented here represents the phase point. Similarly, you can find if a motion of a particle is represented there, this is a symbolic representation of some phase space or mu space, you can say. Then what is the phase space? Phase space is 6-dimensional. If you consider delta x, delta y, delta z are change in coordinates along first, second and third coordinate system, corresponding momentum change is delta px, delta py and delta pz. Then what is the cell volume? That is in phase space, that is product of delta x, delta y, delta z into delta px, delta py, delta z. So if you have 3n number of position, this contains 3n number of position coordinates and 3n number of momentum coordinates, so total 6n coordinates in 6D space. And what is the advantage of considering these phase space? Now phase space provides a geometrical framework between statistical mechanics and helps to minimize the abstraction. When we are unable to draw such phase space on a plane, then phase space should be considered purely mathematical concept in that case only. Suppose we have n number of particles and those are in macroscopic state. So the phase space can be divided into smaller elements. You can find these are the small elements. If you consider this is P and Q, you have read the Lagrangian formulation where we have represented the system instead of X and Y, we have represented coordinates as Q and momentum as P. So the Hamiltonian is a function of H, is a function of P and Q. So this is your P space. This is a 2-dimensional phase space divided into large number of cells. You can find this is a phase space. This is dq represent your dx, dy, dz, and p represent delta px, delta py, delta p. Here you have written this is dp, small change in momentum. This is small change in coordinate system. So what will be the volume? Volume of one cell will be, this is dq into this is dp. So volume becomes dq into dp. This is 2-dimensional phase space. And this symbol signifies the product of all terms, or in one word we say this is the sum of continuous product. Then we will come across the very fundamental question of statistical mechanics. What are macroscopic and microscopic systems? So what is macroscopic and microscopic states? Remember, a macro state is specification of number of particles in each compartment of a system. Suppose we have 4 particles in 2 compartments. So how these 4 particles will be represented? In one compartment there is 0, in other compartment there is 4. Or you have in one compartment there is 1, in other compartment there is 3. Or you have 2-2 arrangement, or you have 3-1 arrangement, or you have 4-0 arrangement. These are called macro states of distribution of particles. That means we have 2 compartments and we have n particles. Then what are the number of macro states? The macro states will be n plus 1. Because in 4 case you have found, if you have 4 particles in 2 compartments, you have 0, 4, 4, 1, 3, 2, 2, 3, 1, 3, 4. There are 5 states. Similarly, for n particles, there are n plus 1 macro states. What are microstates? Microstates are different arrangement of particles in a macrostate. That means if we consider a representation of large number of particles in a large number of particles, then it can be represented in a macrostate. If you made it smaller, keep a division, divide it by some parts, and keep it different cells, different compartments, then we say each compartment belongs to a microstate of the large macrostate systems. So many different microstates are possible from a single microstate. This is an example. Suppose there are 3 cells in phase space labeled 1, 2, 3. And 2 particles AB enumerates the different macrostates. So what are the possibilities? If you have cells in this manner, then you have AB. Other condition is there is 0. This is 0, this is 0, this is A or B, or this is B or A. Similarly, in these are the macrostates contains large number of microstates for a n particle system. This is an example of a 3 particle system. Then we will come across, if we have total energy E of a macrostate, then how the total amount of energy is expressed for microstates. Similarly, if you have n number of total number of particles is n, that can be represented in I number of microstates, and each state have ni number of particles. And corresponding energy, if each particle has energy epsilon I, then total energy is sum over I ni epsilon I. Then this is we can represent this, the total energy, total volume, total number of particles, total chemical potential of the event as a function of some probability that defines the macrostate. Similarly, a macrostate is represented in statistical mechanics. A macrostate is represented by number of particles n, volume v, and E. This is called thermodynamic probability, or some words statistical weight is used. So what is thermodynamic probability? If you denote this by a letter omega as a function of n, v, and E, it can assume a very large value. The minimum value is 1, which is related to entropy. You will read entropy. So for a many body system, so remember, omega represents thermodynamic probability or statistical weight that represents dependent on number of particles, volume, and energy of the particle. Next we come across the macroscopic consideration of many body problem. We have read the Hamiltonian equation in our classical mechanics. The Hamiltonian mechanics are more convenient formulation to describe the statistical mechanics, remember. In classical statistical mechanics, if we have n number of particles and degrees of freedom of each particle is f, then the system as a whole can be represented as S is equal to frequency multiplied by number of particles Fn. So the Hamiltonian equation having coordinates P1, P2 up to Ps, these are momentum coordinates, and generalized coordinates Q1, Q2, Qs. that can be written as by Hamiltonian equation, that is dqi by dt is del h by del pi. And del pi by dt, that is minus del h pq by del qi. This form the system of 2s first order differential equation, remember, where I stands from 1 to this. So this 2s number of differential equations, and we know the simple Newtonian equation of motion, that is the mass into acceleration in terms of generalized coordinates, m d square qi by dt square is minus del u by del q. So what is Hamiltonian? This is your kinetic energy term and this is your potential energy term, which depends on the configuration of the system. And we have in classical mechanics, we cannot generalize the easily the rotational molecules, which have different degrees of freedom, and the corresponding quantum states are able a deterministic way, which is not possible in classical mechanics, because wave function helps us, which is not possible in your phase point or phase space or in representative space, that is possible in case of your wave function. So we consider this, the state of a particle. To represent the state of a particle, we need a phase space. It is a purely mathematical device that is written as dqp into dqqd to the power 3q. D to the power 3q is your dx, dy, dz, or delta x, delta y, del z. And dp is pxq, pyq, pzq, or delta pxq, delta pyq, delta pzq. And in a two-dimensional hypothesis space, the space we define in phase space, and a corresponding point is called your phase point. And it has 6n dimensional space. The phase space is also called gamma space, represented by gamma space, and specified by only those quantities which can be determined for macroscopic measurement without any reference, whatever may be the microscopic details. Now, some of the questions you have to discuss: what are the possible macro states if you have total number of degrees of freedom is 5, and there are they can represent in two ways. One has 3, other has 2 degrees of freedom, and they have 10 n dimensional space. You can find it. Then what are possible macrostates? You can have these particles. You have 10 number of particles. These are 10 macrostates, and one microstate is associated with each microstate. Similarly, when you consider a linear harmonic oscillator, you know another example. A linear harmonic oscillator, the phase space is represented by this one. This is your momentum. Momentum is √2 over 2me, and the coordinate q is √2 over 2e by m omega square. So we know this equation, q is equal to a cos omega t plus phi, where a is amplitude and the total energy is this one. And corresponding momentum, which is mass into velocity, that is m dq by dt, m a omega sine omega t plus phi. So what we consider? We consider if you add these two equations, this is a very nice equation, elliptical equation of phase space is an ellipse. You can therefore find this equation, this is ellipse, having semi-major axis and semi-minor axis. The equation of the ellipse, that is x square by a square plus y square by b square is equal to 1. And you obtain this equation, what you got? In phase space of a harmonic oscillator, you got the equation x is your q and y is your p, that is coordinate and momentum. and the constant semi-major axis length is 2e by m omega square. Omega is the angular frequency of harmonic oscillator, and corresponding b is represented by your 2me. So the quantum theory, we generate those axes A and B. So let us consider the equations in this manner, that the particle having one dimension, how we can represent, confined in an interval 0 to L, confined it in an interval 0 to L. Now is it clearly visible? Okay, then the particle have energy that varies between these two, root 2 over 2me to minus 2me, and the energy variations, you can find how it vary, how these variations of energy takes place between E and E plus delta E. So if you consider each particle have certain energy plus mu b, mu is spin aligned with the particle, then you can find the energy of the system that becomes, takes in these values. So these are particles with energy plus mu b, these are particles with energy minus mu b. What is the number of particles? That is combination of n and m. This is the permutation and combination relations. Next we will go to, this is all about unit 1, the second unit of our basic concepts of that is probability distribution and entropy. So in this case we have introduction, expected learning outcomes, discrete probability distribution, binomial distribution, moments of binomial distribution, Poisson's distribution, moments of Poisson's distribution, continuous probability distribution, moments of continuous distribution, Gaussian distribution, central limit theorem, derivation of central limit theorem, entropy and probability. We will discuss these cases. So let us come to what we have read in previous unit. In previous unit, we have only given some terminologies related to this, that is permutation, combination, phase space, your probability, combining, all these things have been discussed, some facts about macrostate and microstate. We have also given your probability function, we have discussed. And in this case, we established the probability as a mass function of binomial distribution. Remember, very important point, probability mass function of a binomial distribution, and obtain mean and variance of the distribution, establish large number of binomial distributions and Poisson's distribution, will express probability density function as Gaussian distribution. So moments of Gaussian distribution using characteristics function and cumulant generating function, we will discuss the central limit theorem. And now, before going to that, we will say what is the discrete and random variables and what are continuous random variables. Discrete random variables, we take an example. Suppose we have 6 faces of a dice and 2 faces of a coin. So these are the random outcomes of the dice. 1, 2, 3, up to 6, or 2 faces, head or tail. These are random outcomes. If you consider velocity of an atom or energy of hydrogen atom in unbounded state, this is a continuous random variable. Remember, appearance of 1, 2, 3 in a dice or head or tail, these are treated as discrete random variables. Appearance of, but energy of hydrogen atom in unbounded state is a continuous random variable. So while discussing this, we will consider the binomial distribution. We know binomial theorem. but we have to take binomial distribution. You go through it, you have books. I am just telling, binomial distribution is a distribution that you must that indicates the probability distribution. What it tells, if P is the probability of an event A, remember, P is probability of event A, that is an outcome of some experiment. Event A means outcome of some experiment. And Q is the probability of event A that is not happening. So happening is P, not happening probability is Q. Or you say, if A and B are two possible outcomes, then probability of outcome A is P and probability of outcome B, we have told this will be 1. So what is probability of not obtaining? That is Q, which is equal to 1 minus P. Let us assume n similar systems where n denotes number of systems with outcome A and R denotes number of systems with an outcome B. Since we are considering n systems, the outcome may be assumed to be independent events. Remember, mind this word, the systems are independent events. So probability of n such events, n such systems are written as P is written n times, Q suppose arises R times. That means these are favorable events. These are not favorable events, or these are events which are expected. These are not expected. So they can be written as P to the power n, n times P occurring, and Q each occurs R times. That is Pn into Qr. But what is n plus R? N plus R is your n. So you can represent Pn into Q to the power n. And the probability, the arrangement of probability can be written in this manner. That is P of n is combination of n, P to the power n, Q to the power n minus. And this coefficient combination NCn is n factorial. N is the total number of probability, total number of events to occur, and n number of events, that is P, those are favorable events, and n minus n, this is unfavorable events, that factorial. So you have to remember this. What is probability of obtaining P events? Means n events which are favorable events. That is NCn, P to the power n, Q to the power n minus 1. Here, the order of the arrangement is not important. So Pn is called probability mass function, or in short PMF. Remember, Pn is called probability mass function, that is NCn P to the power n Q, this one. This is called probability mass function. If we say it n corresponds to some variable x, then P function of x is equal to n, or you can write simple Px, that is nPn, P to the power n, Q to the power n minus. One example is there. If you have 6 fair coins, obtain probability of getting 4 heads. We have 6 coins. So you throw it different times. And what is probability of obtaining 4 heads? We know probability of head or tail is half. So if you have 6 coins, n represent big N, bold N is 6, and number of obtaining is 4. So just you put in this formula and you calculate probability of obtaining 4 heads is only 0.23. That is, in this formula, n factorial, bold N factorial divided by small n factorial by n minus n factorial, you multiplied by half to the power, half is probability of head, and to the power 4, and probability of tail will be 2, up to 6, half to the power 2, so this is equal to 0.3. So if you look into it, if n is 0, what will be P0? Then you calculate this will be Q to the power bold N. N means the heads, number of favorable events. Similarly, if n is 1, then P1 is this. N is 2, then you have this. We can calculate in this manner. Large number of probabilities can be obtained by binomial distribution. Hence, the binomial distribution of favorable events and non-favorable events having n number of requirements, n number of particles, is represented as q to the power n plus nc1 p1 q to the power n minus 1, so on as binomial distribution function you have read earlier. The shape of distribution can be described by the moments of binomial distribution. This important is moments. We consider mean in quantum mechanics called variance. Mean of this is called moments of binomial distribution. Above is binomial distribution. Moments are explained as expectation values of powers of the random variable of the deviation of the mean. Remember, this is an important concept. There are 4 types of moments. Remember, what are moments of binomial distribution? Moments of binomial distribution represents expectation values. Expectation values, you have remembered expectation value of s integration minus infinity to infinity your psi star x psi x dqx divided by normalized. If normalized, that is 1 in the denominator. Similarly, there are 4 types of moments of binomial distribution. Suppose x is a variable. Then expectation of x is your first variable, is your first moment, that is called mean of x. Expectation value of x is mean of x. If it is in the second manner, if it is variance, it is not mean, it is variance, then this will be expectation of x square. If we consider, what does variance represent? Variance measures the spread of dispersion of the distribution. Remember, mean represents central location of distribution. Variance represents the dispersion of distribution. Then expectation of xq is another moment. It represents the skewness. Xq expectation is skewness. And x4, the 4th moment, that represents your kurtosis. So we have 4: mean, variance, skewness, and kurtosis. These are the 4. Let us consider a variable x. Then how can we calculate its mean? Represent. So here, if x is assume alpha possible distinct values, x have alpha values, that means x1, x2 up to x alpha. So how mean is calculated? First moment of binomial distribution. 2, that means x1 variables occur n1 times by n1 systems, x2 variables occur in n2 systems, and x alpha variables occur in n alpha systems. Total number of systems is n, that can be extended up to infinity. So mean of x is the summation n is 1 to alpha nn x by n, which is Pnx. And you can find this can be represented if fx is any function of x, then mean value of the ensemble average of the function can be written as mean value of fx is your Pnfxn. You can use Pnfx, that n varies from. If fx is any function of x, mean value of the function can be also written as g of x is Pngx. Similarly, if you add these two functions, a mean of f of g, that will obey the your addition principle. Sum of two mean of two functions f and g is equal to sum of individual means, that is sum of f plus sum of g. This shows that mean is a constant with the function. If you take mean, fx is a function. If you take mean of the function and you multiply a constant, c of fx is your Pn Cfx. So c will be outside. C of fx, mean of Cfx is c of fx. So it obeys a constant is multiplied with a function, or the mean of a function, then that constant comes out and we consider the mean. See, constant times that function. Similarly, if fx is a function of x and gy is another function, then we represent f of x, the mean of fx gy is summation n is 1 to alpha pn, r is 1 to beta pr fx gx. Since functions are independent or uncorrelated, we can separate the functions and write their mean. In which manner? Now we can write fx gy, mean of fx gy is mean of fx into mean of gx. This shows the average product is equal to the product of their average. Suppose there is a variance. Delta x is the deviation or the variance of mean values. Actual value is x and mean value is expectation x. So what is the variation? Variation is the actual value minus mean value. Delta x is x minus x expectation. So delta x can be written as x minus expectation of x, that is x, that is your expectation of x minus expectation of x, that is expectation of x minus expectation of x is 0. So the deviation or all possible values of x of about the mean value, that will be 0. Similarly, if you consider delta x square expectation, that is variance, then you will find that is x square expectation minus x expectation square. You have read it in your quantum mechanics in your BSc stage. That is represented here how delta x square becomes x minus expectation x square. And we consider delta x square expectation, that will come across x square expectation minus x expectation times x minus expectation x square. And this right hand side is defined a quantity called variance or dispersion. I have told you the delta, which is represented by sigma, where sigma square is delta x square, is known as variance or dispersion. And we can see that the variance can never be negative. That is one point. This never be negative and lies between 0 to 1, because probability lies between 0 to 1. And in all possible outcomes of Excel are equal to the mean of X. All these variance calculations, skewness calculations, or quartis calculations depends on the mean value. So this sigma square will have the dimension of variable x square, and the standard deviation is represented by this formula, that is sigma is equal to Pn of x minus expectation x square to the power half, because sigma square is this one. This sigma is, what is sigma? Sigma represents the standard deviation, and sigma square provides the value, the measure of deviation. So let us have an example, that is so that binomial distribution x, the expectation value we you will calculate this x as this one, np combination of x minus 1 to n minus 1, p x to the power minus 1, q, and so on. So when you apply this binomial theorem we have stated earlier, you will come across the same topic, that is the mean of x will be your np of p key plus q to the power n minus 1, which is also, because this is 1, so this is your np. Because p plus q is 1, so the 1 to the power n minus 1 is 1, this is np. Similarly, the variance of binomial distribution of sigma square, which is equal to x square expectation, can be written as minus expectation x square expectation minus this, which is equal to np cube. That means sigma square is np cube. So what is sigma? Sigma is the root over this one, and sigma by x expectation will be npq by np, because we know from the previous example x is expectation of x is np. So this gives a value 1 by root over n root n. This is standard deviation or variance. Standard deviation divided by per mean is directly inversely proportional to square root of n. That means if you increase the standard size, the standard deviation will automatically decrease. So we also, when we plot the graphs, the example, when we plot certain graphs in case of physics while obtaining the experiments, we do find the standard deviation decreases. The more we choose the graph size, the plotting size, the less will be the standard deviation. If you take the less, the standard deviation will be more. This is all about your binomial distribution and movements of binomial distribution. The another two are Poisson's distribution and Gaussian distribution. We will discuss now Poisson's distribution. So Poisson's distribution is a discrete probability distribution. What is Poisson's distribution? It is a discrete probability distribution. Remember, Poisson's distribution is a discrete probability distribution. It expresses probability of a given number of events occurring in fixed interval of time or space. Once again, Poisson's distribution is discrete probability distribution that expresses the probability of a given number of events which occurs in a fixed interval of time and in fixed space. That means it occurs in a constant mean rate and occurs independently with time. We can say the probability, suppose we have X events. Then what is the probability of observing X events? That is written by this one, probability of X events, where X is equal to K, that is event for K is the actual number of events, that probability of X events or K actual events. That is, if per event lambda is represents the mean of each event, then probability of this is lambda to the power K e to the power minus lambda divided by K factorial. So Poisson's distribution is represented by this one, P, the probability of actual number of events. P is a function of probability of actual number of events, that is lambda of K e to the power minus lambda divided by K factorial. This means what is lambda? We have lambda is a new parameter, and it is equal to n times. N means the total number of times the events multiplied by your P, and it represents the mean of binomial distribution. So the probability distribution, if you consider the probability of X is n factorial by X factorial n minus X factorial into lambda by n to the power this into this one, and upon n tends to infinity, this term 1 by lambda minus n, this becomes e to the power minus lambda. Hence, the above probability function takes the shape px e to the power minus lambda, lambda to the power x by x factorial, n factorial divided by n minus x factorial into this one. But he used Starling's approximation that n factorial is n to the power n e to the power minus n root over 2 pi n in this one, in your numerator. Then you will obtain the limiting case of this, your Poisson's distribution function go up to takes the shape e to the power minus lambda, and this factor is equal to 1. So the probability function, probability mass function is written in terms of your Poisson's function as e to the power minus lambda, lambda to the power x by x factorial. This distribution is called Poisson's distribution. And this shows if when n is large, the binomial distribution, when n is infinity, remember this is your Poisson's distribution becomes or converges to binomial distribution, or in other words, binomial in which condition Poisson binomial distribution converges to Poisson's distribution. Now when we have a very large behavior, value of n is very large, Poisson's distribution becomes equal to this, becomes equal, converges to binomial distribution converges to Poisson's distribution. And in this case, when we consider the Poisson's distribution, then what is the sum of probabilities? In case of Poisson's distribution, the sum of probabilities are expressed as x is 0 to infinity, p of x e to the power minus lambda, summation x is 0 to infinity, lambda to the power x by x factorial, which is the normal, and this is equal to 1. This is your normalization condition. You have read normalization condition in wave functions. Psi star x, psi x, dx or dqx, whatever it is, dqr is equal to 1. So, Poisson's distribution, sum of the probabilities is 1. Always we have told you 100% is the probability of finding a particle. As we have read, in case of binomial distribution and moments of binomial distribution, similarly, we will read in the next heading, that is moments of Poisson's distribution. Moments of Poisson's equation indicates the mean and variance of Poisson's equation. We know by definition the mean variable of x. The mean of x is 0 to infinity x px. That is e to the power minus lambda, x is 0 to infinity x lambda to the power x by x factorial. That is lambda e to the power minus lambda x lambda to the power x minus 1 by x into x minus 1 factorial. So mean of x, you represent lambda e to the power minus lambda. This is lambda x to the power minus 1 by x minus factorial, x cancels. So this is lambda e to the power minus lambda. Under limiting condition, we have seen this value is equal to e to the power lambda. So this is lambda. This proves that the parameter which we have chosen lambda is the mean of the distribution. What does it indicate? Lambda is mean of the distribution. We have told you the moments, 4 moments, x expectation, x square expectation, mean, variance, skewness, and quotients. So now this is mean of this Poisson's distribution, moment of Poisson's distribution. The next moment is your variance. Variance, you remember in binomial distribution, we have expressed as sigma square, that is x minus expectation of x minus x expectation of square, which is x square expectation minus x expectation square. So the variance can be written as, this can be written as e to the power, in terms of Poisson's representation, this is e to the power minus lambda into x square, lambda to the power x by x factorial. Let us rewrite this term. How can we write x square? I can write x square as x plus x into x minus x, that means plus x minus x cancels. Similarly, in terms of here x square, we can write this term. Then what is our variance sigma square? Sigma square becomes equal to e to the power minus lambda x of x into x minus 1 lambda to the power x by x factorial minus lambda square. So what is sigma square? The sigma square, if you take x, this value, this is your x square term, x into x minus 1 term. So this value, sigma square, is e to the power minus lambda x of this one plus e to the power minus lambda, lambda square, lambda of this one, minus lambda square. So what does it indicate? This is your lambda. This is lambda square minus lambda square. This cancels. Hence, total value sigma square is equal to lambda. What does it indicate? This indicates for a radioactive substance, this indicates the standard deviation for Poisson's distribution sigma. If sigma square is lambda, sigma is root lambda. That means the first and second moments, that is expectation of x and x square expectation, have the same value lambda. You have seen in the first case, what is your expectation of x? Expectation of x is your lambda, mean of x, and the variance in Poisson's distribution, sigma square is lambda and sigma also lambda. So both are same. That means in case of Poisson's distribution, the mean, that means first moment of Poisson's distribution and second moment of Poisson's equation, that is standard variation, is remains same and equal to lambda. So now let us have an example. Let us consider a radioactive substance and it emits alpha particles, and those number of alpha particles are counted in 2 minutes. So what is the probability of observing x number of alpha particles, that is x is equal to 1, 2 and 3. Here we can say that we have 2 minutes t and a rate is 1.8 per minute given rate of emission of alpha particles. So what will be lambda? Lambda will be your RT, that is 1.8 into 2, that is 3.6. What is our probability distribution function in terms of Poisson's distribution? That is Px is e to the power minus lambda, lambda to the power x by x factor. So what is the first particle? What is the probability of obtaining first particle? That will be your P of x, which is e to the power, lambda value is 3.6 by 3.6 factorial into this one. Similarly, you can calculate for x is equal to 2, x is equal to 3. So this is the probability of observing first alpha particle, second alpha particle, third alpha particle. And you can find what is the probability of finding first alpha particle is 9.8%. If you calculate putting x is equal to 1. And second one is 17.7 and third one and so on. So the Poisson's distribution function and their moments gives us the idea about calculation of probability, even if we are unable to calculate by means of some experimental cases, because radioactive experiments cannot be calculated by an observer nearer to that place. So by statistical applications, we are able to exactly calculate how many number of particles are possible in that case. Then our distribution, these are all random probability. Let us look on continuous probability distribution. Continuous probability distribution, we have discussed that in this case, the random variables which occurs, I have told you the energy of unbounded hydrogen atoms, they represent continuous distribution systems. Suppose we focus on a small interval x to x plus dx. So what is the probability within the interval dx? So probability within a function x to x plus dx is called probability density function and defined as px is equal to dpx by dx. If all the values of x are equally likely, then the probability of finding x in the interval is written as a1 to a2 px dx. So probability of density function is normalized. If it is not normalized, then it can be normalized. Probability density function. In a sample space S, what is probability density function? S represent the sample space, and probability of px dx integration over sample space S is equal to 1. That means px probability density function have a dimension of x to the power minus 1. If probability density function can be integrable and can be normalized, so obviously it represents, since this is an integral part, we have considered the summation part, that is your discrete functions. For this continuous function, for representing multidimensional continuous random functions, we take help of this integration. Then we must discuss moments of continuous distribution function, as we have discussed for binomial and for your Poisson's distribution function moments. So the mean value of for continuous distribution function is expectation or mean of x continuous distribution function is x. This is your px dx is 1, and the interval for continuous functions ranges from minus infinity to infinity. So in this case, we define the mean value of x can be written as fx. The x is represented by fx, where fx represents the mean value. And we say the nth moment of variable x is represented as x to the power n. So x to the power n can be written as x to the power n nth moment, that is x to the power n moment is minus infinity to infinity x to the power n px dx. The moments of the variable x can be obtained by method of integration for a given probability density function. We have discussed the method where the function is known as characteristics function. Characteristics function is used to determine the moments of continuous distribution function. Please remember, for determining the moments of continuous distribution function, we take help of characteristics function. And the variance we know, this is your x first one, the variance, that is sigma square, is your x minus expectation x square expectation, which varies from minus infinity to plus infinity. That is x minus x expectation square px dx. We know that standard deviation is the square of root of variance, square root of variance. That's why the nth central moment can be written as x minus expectation x to the power n raw expectation, which is equal to, this is function, so this is f times n px dx. This is about your continuous distribution function. Next distribution, we have discussed binomial distribution, we have discussed continuous distributions, we have discussed Poisson's distributions. Now we have Gaussian distribution. Now, you can ask Lily Puspa, you have raised hands. Lily Puspa, are you audible? Okay, anyway, next is Gaussian distribution. You have read your Gaussian distribution function. in
डिस्प्ले दिखा के पढ़ाते तो अच्छा होता है, ऐसे सुनने से ज्यादा हम लोग डिस्प्ले को देखते तो पढ़ा रहे तो ज्यादा
आपका
बेहतर।
पास है तो आपका पास मटेरियल है, आपका पास मटेरियल है ना, सो इसलिए मटेरियल है तो अच्छा है। आप जाइए वही मटेरियल्स को तो इग्नो ने शेयर किया था ना आपको।
सर आप कौन सा पार्ट पढ़ा रहे हैं सर आज फिजिक्स का?
फर्स्ट ब्लॉक
सर
वन
फिजिक्स का कौन सा पार्ट
स्टैटिस्टिकल
चल रहा है?
यूनिट 2 गॉसियन डिस्ट्रीब्यूशन
सर
2.3.2
एमपीएच
जी।
कितना सर नंबर? एमपीएच
जीरो
एमपीएच
वन वन
कितना?
011
11।
statistical mechanics.
ओके।
Then this is Gaussian distribution function. There are many distributions such as Poisson's distribution, Gaussian distribution, Lorentz distributions. For a physicist, the Gaussian distribution is most important distribution. Gaussian distribution is the most important distribution, and you are familiar with the Gaussian distribution. How can we represent Gaussian distribution? The Gaussian distribution can be represented as Gaussian distribution can be represented in this manner that if that is the probability of Gaussian distribution function, Gaussian and probability density of the Gaussian distribution function is written as rho of x is 1 by 2 pi sigma square expectation of e to the power, that is e to the power minus x expectation square divided by 2 sigma square, where sigma square is the variance and 1 by 2 sigma square represents the here normalization constant. This is the normal curve. This is Gaussian distribution function. And this is sigma 1 is less than sigma 2. When sigma 1 is less, this is the peak of the Gaussian function, is the width decreases, and this is more sharper than sigma 2. So Gaussian function depends on the variance. Sigma square is the variance that depends on the normalization factor. Now on the mean of this x mean is mu, so the distribution may be written as p of x is 1 by sigma times your 2 pi expectation of x minus mu square. But is here mu1 is mu2. This shows, this figure, what does it indicates? The probability of this Gaussian distribution function, which is equal to x minus mu square by 2 sigma square, and taking mu to be 0, this is 1 by sigma minus sigma root over 2 pi expectation of this one. So what does it indicate? The width of the Gaussian distribution function, which is equal to 2 sigma. It clearly indicates the larger the standard deviation, the larger the width of the curve. That means the more the standard deviation, the more is the width of the curve. This depends on x. So the mean of the variable x can be written as integration minus infinity to infinity x px into dx. So expectation of x is 1 by sigma into root pi minus infinity to infinity x expectation x minus mu square by 2 sigma square into dx. Since we have considered the mean to be mean of x is mu, it is obvious that the RHS value gives is equal to mu. So we have expressed the mean deviation in terms of our Gaussian distribution function. Suppose let us have an example. The example is what the month we will consider our home. In our home, what is monthly demand of a commodity, such as rice? What is demand of rice or dal in our house? It is a continuous variable because we always need rice or dal or vegetables. So the probability, we can represent the probability density in terms of 2 in either it is 2 into x minus 1, where x lies between 1 and 2, And another probability is 0, that is elsewhere. So obtain the mean and variance. This is the probability function. You obtain the mean and variance. So what is the solution? You obtain the mean value is what is the formula? X is equal to integration 1 to 2. You have given here. It is not minus infinity to infinity. What is the value? The value x value lies between 1 to 2. So integration 1 to 2 x px dx plus your 0. Second one is 0. So 1 to 2, this is 2 times x px. It is 2 into x minus. So this is 2 times x into px is your x minus 1. X into x minus 1 dx. When you integrate, what is this? This is 5 by 3, which gives mean distribution is requirement is 5 by 3. Similarly, you can find x square expectation and x square expectation is your 17 by 6. So you can calculate the variance. What is the variance? Variance is equal to x square expectation minus x expectation square, that is 17 by 6 minus 5 by 3 the whole square, 1 by 18, which is the variance distribution. Now we have a characteristics function. Now we have a characteristics function. The another one, the characteristics function. Remember what is characteristics function? Characteristics function for k number of items is denoted by p tilde k. Remember this p tilde k representation. The characteristic function is the generator of moments of the distribution. Remember what is characteristic function? It is a generator of moments of the distribution. Suppose Poisson's distribution, P bar K is the characteristics function, Gaussian distribution, your binomial distribution, it is the generator of moments. We have read the moments of those distributions, and a characteristics function is the generator of those moments. What do you mean by generator of those moments? That represents the Fourier transform of probability of that function. If Px represent probability function, P tilde x is Fourier transformation. You have read Fourier transformation. If we have nth moment of a variable, let us have an example. Nth moment of a variable is x to the power n, mean, that is minus infinity to plus infinity, x to the power n, px dx. So we can represent the characteristics function, that is p tilde k e to the power minus ikx px e to the power minus ikx dx. So the inverse Fourier transform is p rho px is p tilde k into this one, that is Fourier transform. And when we use Taylor's expansion, you have read Taylor's expansion in case of your classic, your complex, then e to the power minus ix is equal to minus ik to the power n by n factorial into x to the power n. When you use this Taylor's function, so the moments of the distributions of your characteristics function, that is p tilde k is minus ik n by n factorial xn saman minus ik to the power n by n factorial into x to the power n. The moments of the probability distribution function about any point mu can be represented like this: e to the power ik mu p to tilde k e to the power ikx, ik into x minus mu, which happens to be minus ik to the power n by n factorial into x minus mu to the power n mean. So the nth moment is written as x to the power n mean, that is equal to del n by del of ik minus ik to the power n p tilde k. This equation refers, what does it indicate? X to the power n is equal to del n by del minus ik to the power n. This refers nth moment of variable x. So since this refers nth moment of some variable x, so it must be a generator of moments. We can see the nth moment of some variable x can be obtained either by integration, or you can obtain by solving it in a preferable derivative manner. Now the other generating function is cumulant generating function. What is cumulant generating function? Now, we know the characteristic generating function is P tilde K. Now, we can define a cumulating generating function is a generator of cumulants. What are cumulants? Cumulants means the probability distributions are a set of quantities derived from logarithm of characteristics function. Once again, cumulant generating function is the generator of cumulants. What are cumulants? Cumulants is the probability distribution of set of quantities derived from logarithm of characteristics function. And it provides an alternative representation of moments of the distribution. Suppose P tilde K is our cumulating function. What is that one that we have read? Minus ik to the power n, sum over n to infinity by n factorial into mean of x, that is x to the power n mean. So P tilde K can be expanded, and finally the expansion can be, if you take log of P tilde K, then that is a cumulant. P tilde K is your cumulative, P tilde K is your generating function. If you take logarithm of K and you expand it, then this log of Pk, that is minus ik to the power n by n factorial xn, that is xn mean, this is represented with this letter C. C means accumulating function. The mean is for accumulating function. So ln P tilde K is minus ik xc minus ik whole square by 2 factorial x square mean C, accumulating function, and so on. This is the expansion. Here the terms xc, mean of xc, x square c, xqc are called cumulants. So you have used a term C. We have a subscript. C is given because that represent cumulants. So what are cumulants? Cumulants are obtained from the moments of generating function. We obtain a generating function P tilde K, take its logarithm, expand that function, and from the ascending order of the function, the first one is x variant, x mean, that is called your first cumulant, x square mean of or expectation of x square with C subscript is called second cumulant, and the third one is called xq is called third cumulant. Hence we can suggest that P tilde K can be written as 1 plus n is 1 to infinity minus ik to the power n by n factorial x to the power n. So P tilde K can be written as 1 plus epsilon. And what is epsilon? Epsilon is the expansion of this function. You can expand epsilon is this one. This to the power n is 1 to infinity. You put 1, you put 2, and so on. Hence, we can represent this ln P tilde K is ln 1 plus epsilon, that is minus 1 to the power j plus 1 epsilon to the power j by j factorial. So ln P tilde K is written as epsilon minus epsilon square by 2 rho factorial plus epsilon q by 3 rho factorial minus epsilon to the power 4 by 4 rho factorial. So if you rearrange these terms, what will you obtain? Then you will obtain, this is the rearranging terms, epsilon value is this. That is minus ik to the power n by n factorial xn mean of x to the power n. So ln P tilde K is minus, if you take log of this one, then you get minus ik x factorial x mean minus ik square by 2 factorial x square expectation minus x expectation square plus so on. Now you can find for n is equal to 1 minus ik x up to c. This is minus ik x. So x cumulating generating function is equal to x. That means we have proved that when you find cumulative generating function, that is mean of the variable x. That means x ra cumulative is equal to mean of this function x. Similarly, if you have n is equal to 2, you will find x square cumulative is x square expectation minus x expectation square. What is x cube cumulative? That is equal to x cube expectation minus 3x square expectation into x expectation plus 2x cube expectation. So this is called skewness. Then the skewness distribution is a perfect symmetric Gaussian distribution. And the distribution may not always perfectly symmetric. And similarly, you can find the fourth one, that is your kurtosis. The kurtosis can be represented by, if n is 4, x4 cumulative generator, that is x4 expectation minus 4 xq expectation into x expectation minus 3 x square expectation plus 12 times x square, this one. So the Gaussian, in case of Gaussian distribution, we have found that the px is 1 by sigma root 2 over 2 pi e to the power minus x minus mu rho square by 2 sigma square. When you use these cumulative functions and you integrate it, then finally you will obtain the result that you will obtain a result p tilde k is e to the power sigma square k square by 2 minus I k mu, and with a term 1 by sigma into root 2 over 2 pi minus infinity to plus infinity e to the power minus y plus I sigma square k square by 2 sigma square dy. The second term on the RHS is a Gaussian integral, this term. And the Gaussian integral is the moment of generating function of the characteristic function. So p tilde k can be written as e to the power this sigma square k square by 2 minus I k mu, because this term is equal to 1. Hence, the logarithmic of this function, that is cumulative generating function, if you take p tilde k, to obtain cumulative generating function, you take the logarithm you will obtain sigma square k square by 2 minus I k mu, because here you term, here your e to the power something, when you take log exponential cancels, this is sigma square k square minus sigma square k square by 2 minus e k mu. And the log of p tilde k is minus I k square sigma square by 2 plus I k mu. So the Gaussian distribution can be written as del of minus I k log p tilde k at k is equal to 0. So x expectation c is mu plus minus I k c square at k is equal to 0, which is equal to mu. That means the mean of cumulant of a form variable is equal to mu, that is the first cumulant is nothing but the mean of the distribution. Remember, the first cumulant is nothing but the mean of the distribution. Similarly, when you calculate the second cumulant, that is equal to x square, that will be del square by del minus I k square log of p tilde k at k is equal to 0. Hence, from this you find this is equal to the same thing, that is variance sigma square. The variance of the distribution is the second cumulant. Mean is the first cumulant of generating function. Variance is the second cumulant. Similarly, you can find the xq, that is skewness, x to the power 3 cumulant is 0 when n is greater than 3 for a Gaussian distribution functions. So we find the Gaussian probability density function is a completely specified by two cumulants. Gaussian distribution function have two cumulants. One is x expectation c, which is equal to mu, and second one is x square expectation cumulant is your variance, that is equal to sigma square. And now we will go to central limit theorem. What is central limit theorem? We will go to the central limit theorem. What is its statement? The statement is like this: central limit theorem, that central limit theorem or CLT. Let us consider any system with any distribution function. It may be binomial, Gaussian, Poisson's, or Lorentz. What is statement of central limit theorem? It states that when a sufficiently large number of similar systems are sampled, the resultant distribution is always a Gaussian distribution. Remember, what is statement? When sufficiently large number of similar systems are sampled, the resultant distribution is always a Gaussian distribution. That's why we can suggest that when the probability of the distribution was taken into consideration, the Gaussian distribution represents a sampling of large distribution systems which are now can be calculated by considering some mathematical preliminaries. Let us consider two random systems. Two random variables are x and y. When you try to prove this, rho x represent probability of finding the variable x and within a range x and x plus dx. Similarly, rho y dy represent the probability of finding the function within the range y and y plus dy. And the rho phi z dz represents the probability finding z and dz. So what is phi tilde k, the characteristics function? We have considered earlier p tilde k. Here we considered phi tilde k. This is the expectation of e to the power minus ikz. And that is equal to integration over xy because it is a continuous function. So integration over x and y, e to the power minus ikz px qy dx dy, where z is equal to x plus y. And this phi tilde k is equal to p tilde k into q tilde k. Represent, we have two functions x and y. So when you take these two functions, the product of their, that is p tilde k into q tilde k, this represent your new function, that is your phi k. This is your central limit theorem. Then how can we derive central limit theorem? We have to consider n variables, x1, x2 up to xn, big N. And the mean of this function can be sum of mean of the function can be represented as x, which is equal to x1 plus x2 plus xn divided by n. Then we say, what is phi of s? A Gaussian distribution probability density function, we represent phi of s is 1 by 2 pi sigma s square minus s minus x expectation of whole square divided by 2 sigma s square. So when you consider the random variable x1, x2, xn, those random variables, you can multiply. What is phi tilde k? That is same one, integration over x1 e to the power minus ik x1 by n rho x1 into dx1. Similarly, for second one is x2 rho x2 dx2 with the same constants. Similarly, for n, this is rho xn dxn. When you multiply these functions, what do you obtain? You obtain the result. The result is the sum phi of k is equal to 1 plus r to the power n, where r is equal to minus ik by n into x1 expectation minus ik by n square into x square expectation by 2 plus so on. All these terms are neglected. So the function phi tilde s, sum of these functions, is your 1 by 2 pi phi tilde k e to the power ikx into dk. In this manner, you can by avoiding the algebra, I am avoiding the algebra, you can obtain the sum becomes equal to S, which is equal to sum over xi by n, that is equal to expectation of x, sum over I, xi expectation divided by n, which is equal to expectation of x. So sigma x square is x square by n. Hence, central limit theorem ensures that despite complex and potentially non-Gaussian distribution of individual particle behaviors, the behavior of large number of particles and large number of systems can be predicted with Gaussian distribution functions. So this theorem simplifies and analyzes how we can understand a macroscopic phenomena. That is your central limit theorem. Now we come across entropy. You all know what is entropy, the disorderness of the system. If ds is change in entropy, this is represented by a thermodynamic variable dq by t. And how we can represent entropy? With the probability. S is the entropy, say S is a function of P, and it measures the disorderness of the system. You have read in your BSc stage that entropy, which can be approximated by Stirling's approximation, is represented by that Stirling approximation, that is ln n factorial is n ln n minus n. So if you represent omega, the density function omega, that is n factorial, by sum over continuous product I is 1 to 6 into n1 factorial. And considering the Stirling's approximation, you will obtain a relation that log of omega is S divided by Kb. So the macrostate entropy is related, that is thermodynamic probability omega, log of thermodynamic probability is S by K beta. S is your entropy, K beta is Boltzmann's constant. So entropy is initially invented by Boltzmann. Okay, that's why Boltzmann's constant. So this is S by K beta, and S by K beta is nothing but as per your approximation and the previous relation, this is n log n minus ni log ni. When you simplify this, you finally obtain the relation that S by K beta is minus n sum over I pi log pi. So this is called Shannon's form of entropy, that is S by K beta is minus n pi log pi, Shannon's form of entropy. This gives a direct relation between probability P and entropy S. S by K beta is minus n times sum over I pi log pi. This is all about your probability and your thermodynamic relations. Now the next one is, what are the third unit? You will go through the third unit, which have to discuss about thermodynamics and statistics, how they are correlated. Okay, in this unit we will discuss on entropy maximization with Lagrange's multipliers, discrete distribution, and what is relation between thermodynamics as well as statistical mechanics. What is Maxwell-Boltzmann distribution partition function, thermodynamic variables, and principle of equal a priori probability. So while going to it, we will first discuss on entropy maximization. Entropy maximization by considering Lagrange's multipliers. You have read Lagrange's multiplier in your +3 first year mathematical physics first course, calculus, variation of calculus. To what is Lagrange's multipliers? When some function is not exact and its solutions are unavailable, we multiply a factor lambda and we are able to obtain the solution and we got the exact differential equation. So the same method is utilized here, the Lagrange's multiplier method, it converts the constraint optimization problem into constraints into a form of constraints and directly incorporate the function through additional variable called Lagrange multiplier. What is their variable? That is lambda. We know a Lagrange's function. We introduce Lagrange's multiplier lambda j, and for each lambda j there is a constraint gj. The Lagrangian function lambda L is a function of x1, x2, xn, lambda 1, lambda 2, lambda n. So this can be written as f of x1, x2 Lagrangian function L, or simply you can say x is a function of x and lambda is equal to f of x1 to xn minus lambda into multiplied by gi. What are gi? Gi are constraints. Lambda is Lagrangian multiplier. So this equation is very important. L Lagrangian, which is a function of x lambda, is a function of x1 to xn minus lambda j gj x1 to xn. So under critical condition, you know the Lagrangian L. Lagrangian L, if L is the Lagrangian, then critical condition, then del L by del xi is equal to 0. And del L by del lambda is equal to 0, where I varies from 1 to n. And now you can suggest that in statistical mechanics, when you consider certain critical points, we deal with the second order differential equation, the conditions, second order differential equations especially. So in one word, we say the Lagrangian is equal to f of xy. Lagrangian, which is a function of xy lambda, is now becomes a function of xy minus lambda multiplied by, lambda is a multiplier, lambda multiplied by the constraints g multiplied with, g is a function of xy. Lambda x L, which is a function of xy lambda, is f of xy minus multiplier lambda times g of xy, where g are constants. So we find the derivative del L by del x, and that becomes your del f by del x minus lambda del g by del x. Similarly, you find del L by del y, and del L by del y is equal to 0. So what we find? Then we find del L by del x is equal to del L by del y. That is the equation of exactness. You remember the equation of exactness? M dx plus n dy is 0. Then del m by del x is del n by del y. That is exactness. Similarly here, L is equal to f of xy minus lambda times g of xy. Then del L by del x is 0. Del L by del y is 0. So del L by del x is del L by del y. Now the equations becomes equal to, by using Lagrange's multiplier method, we find these are what? Exact solutions. Hence, we can use one method, Lagrangian method, to get that entropy is maximum or maximum energy distribution can be obtained by multiplying a factor lambda with constant gi. We define to obtain maximum multiplications. We obtain the relation that lambda, a function Lagrangian, which is a function of x1, x2, xn, and y1, y2, yn is equal to f of xy minus lambda times g into this one, which satisfies the equation del L by del x is del L by del y. Hence, Lagrange's multiplier can convert the maximization of entropy. Next heading is discrete distribution. When you come to discreteness, you remember always integration is converted to summation. And the reverse occurs when you go to continuous distribution. Let us consider there are a dice. A dice has k number of faces. We do not know it has 6 faces. It has k number of faces. So what is the probability of normalization? The probability of normalization condition, that is I is equal to 1 to k pi. What is maximum probability? That will be 1. We know always the maximum probability is 1. So if we have a constant g according to Lagrange's method, then g, which is a function of pi, can be written as summation I is 1 to k, that is pi minus 1. That means when we use normalized condition, one constant goes out. So total number of probability minus 1 is your number of constraints. And when you use multivariable function, that is f is a function of p1, p2 up to pk, then we define a new function, that is f, which is a function of pi probability, that is entropy S by nk beta. S is entropy and fpi is called maximized function. So we use method of Lagrange's demultipliers. What we have defined? L is equal to f minus lambda g. L যদি function হব pi, তাহলে f হব function of pi, g ମଧ୍ୟ function of pi. ଆମେ ନେଇଥିଲେ L xy is f of xy minus lambda. Here we considered pi into this one. When you solve for the jth variable and apply maximization condition, then del L by del Pj minus del by del Pj of f minus lambda g is equal to 0. When we solve this method by considering the partial derivatives, then the RHS becomes a constant quantity. And from this normalization condition, we define 1 by a sum over I is equal to 1, pi is equal to 1. And a represents the normalization constant, which is equal to sum over I is 1 to n, 1 to k pi, or you can say a is equal to k e to the power minus lambda minus 1. Hence, a function pj can be written as in this manner if you solve it, that is e to the power minus lambda minus 1 by a, which is equal to e to the power minus lambda minus 1. What is a? A value is k e to the power minus lambda minus 1. The numerator and denominator cancels and you obtain pi is equal to 1 by k. So for 1 by k means what is dice? Dice has 6 faces. So what is probability of finding each face? 1 by 6. K is 6. Now remember, by maximization condition, the same thing you are obtaining the probability of finding one face in a just dice play of one dice once is 1 by 6. Probability of finding 1, 2 or 3 or 6 is 1 by 6. Same thing you have obtained in case of using your maximization condition. Hence, we define another constraint. Instead of g, we define another constraint h. H is a function of pi, and what is that? That is summation I is equal to 1 to k sum over I pi minus epsilon. What is epsilon? Epsilon is summation of k number of microstates which varies from I to k, and epsilon I represents energy of each microstate multiplied by pi. So this epsilon is an average outcome of this. Now we define by means of Lagrange's multiplier. Initially we have multiplied a factor lambda and we obtain L is equal to function minus lambda g times the function. Lambda xy is f of xy minus lambda g of xy. G is a constraint. Now we have defined another constant h. So another Lagrange's multiplier is beta. First Lagrange multiplier is alpha. Second, and a constant is g. Now we have defined another constant h, and second Lagrange multiplier is your beta. So what will be my Lagrangian? My Lagrangian will be f, which is a function of pi, minus lambda times g, which is a function of pi. It was initial, and now we introduce another constant, so another multiplier minus beta into another constant, that is h into pi.
Excuse me, sir.
Such that with
Excuse
the
me, sir.
help of
Sir, namaste, sir.
Namaste, sir.
Excuse me, sir. Sir, actually, your slides are not visible and we are not able to understand. But if there is any slide, or we can see whether what is the equation of that, what is the equation, and where is the lambda and where is the summation, that we are unable to know. So can you show in some
No,
slides?
no, I am not using that method. I know the which students it is supplied to the students. These things are given to the students, sir. Okay, it is with you. So we have clearly given that we are using these blocks and these units. Please go through the units. The book is with you.
That means you will have to
Okay.
go through the book and just listen to you.
No, we are giving the doubts, sir. What are the functions? We can see in this manner only, but this is not possible to share that video because it is e-Gyanakos, it is available and the book is supplied to you, sir.
Okay. Yeah, it would be better if you can present the matter through some slides. That will be better, I think.
Slides, I have not prepared slides.
So that means through PowerPoint slides. If you can visualize those equations, then it will be better.
No, it will be very difficult to within short span of time 2-3 days. Okay, it is very difficult to prepare those slides within two
No,
three
it's
days.
okay. It's okay if it is not possible to show complete slides, but we can take equations like that. So from that equations, you can explain all these things. Suppose only
No,
one or two equations you are showing through slides, only
no,
one
you
or two
can
equations you are
see.
showing, then the explanation you can give.
Uh, because of large number of portions to be covered, because here is
That
the
would be
time
better in
we
my
can.
mind.
Okay, we will see in the next. Then this is, you can see here, this is the
Ah,
Lagrangian. That is, initially we have a function f of p1 minus this. We have multiplied another Lagrangian multiplier, that is beta h times pi, and we are able to obtain the same relation. That is, the function becomes an exact differential equation. So in this manner, we can multiply large number of variables, large number of Lagrange's multiplier, and we can solve this problem. Similarly, and this will be useful in your Maxwell-Boltzmann distribution formula. Similarly, in continuous distribution, as in your discrete distribution system, in continuous distribution system, only difference is we define this entropy S, which starts from minus infinity to infinity, rho v log of rho v dv. And the normalization condition gives G nu is this one. In the similar manner, we can project and we can move similar manner. We obtain the expression for your constants of the equipartition theorem, where the energy for each degree of freedom is equal to half kBt. That is half mv square average is equal to half k beta t, where k beta is your Boltzmann's constant. We take the same equation, that is L is f of function of v, lambda g of v. This is a constant h minus beta h of v. In this manner, when we proceed further, we will obtain and we optimize this probability function. We skip some mathematics. We obtain the relation that rho of v is m by 2 pi k beta t e to the power minus mv square by 2k beta t. This is your Maxwell-Boltzmann distribution function of velocities. What it indicates? It indicates in one dimension, we can describe the distribution of velocities in classical ideal gas, which is in thermal equilibrium. And normally, the distribution which is confirmed by the entropy maximization, it indicates the Gaussian distribution is the only maximization distribution value of the entropy. And under a range, velocity range v and v plus dv, we can obtain your equation, that is rho v dv is equal to 4 pi times m divided by 2 pi k beta t to the power 3 by 2 v square into e to the power this. This is the Maxwell distribution formula, which is true for your classical dynamics. Later on, it was modified by Fermi-Dirac statistics and Bose-Einstein contribution, Bose-Einstein gas contributions. Under that condition, we have considered the function in some other manner. Here, we will find that the K beta T, the temperature, plays a vital role between expression of thermodynamic probability as well as entropy of the system. Now, the same thing, this result gives a contact between statistical mechanics as well as thermodynamics. What is that? Both are two fundamental branches, thermodynamics and statistical mechanics. Thermodynamics deals with the macroscopic behavior and with the variables, that is temperature, pressure, volume, etc. And your statistical mechanics deals with the microscopic systems. It deals with the entropy, which is related with the thermodynamic probability, that is S is equal to K beta times log omega. And in thermodynamics, the quantities like internal energy, entropy, and partition functions are there, but partition function was not there in thermodynamics. But the partition function, which was introduced in statistical mechanics for macroscopic and microscopic systems, plays a major role. How? Now, the partition function is explained by, say, Z, which is a function of beta, is equal to e to the power minus beta Z, which is a function of beta, e to the power minus beta epsilon J. So this partition function Z explains the thermodynamic probability of any system. Suppose we have two systems, we want to make a partition, and the probability becomes omega 1 and omega 2. So omega 1 is a function of number of particles, say in first compartment, that is N1, volume V1, energy E1, and in second compartment it is N2, volume V2 and E2, energy E2. So the total energy in this case, E is equal to E1 plus E2, and you can find, if you have these functions, this is a accessible microstate for A1. What are accessible microstate for the system? This is microstate for A2. So from A1, these are the accessible states. From A2, these are the accessible states. Hence, the microstate, that is omega E, which is a composite system of A1 and A2, then the composite microstate, you will consider omega E1 into omega E2 is equal to omega E1 into omega 2 into E minus E1, which is equal to omega of E1. That's why any isolated physical system which left to itself will proceed in such a manner that they will settle down the microstate, which gives maximum number of possible microstates. Hence, the value of energy that we have considered in the maximized microstates, say A1, A2, A3, or A21, A23, and so many states, that is the maximum number of possible microstates which can be obtained from a particular microstate. So Boltzmann give a relation between entropy and, that is S is equal to K beta log omega, which omega is your probability. He considered the average energy value of the equilibrium energy system. Then he took the partial derivative, that is del omega 1 omega 2 by dE1 is equal to del omega by del E1. And using this relation, what he obtained? He obtained this relation that we can obtain the relation by differentiating this function, in a very numerous manner, and by rules of differentiation he obtained he obtained the relation that beta is equal to log omega E by D, where N, V and E are constants. So the parameter beta is nothing but has a dimension of reciprocal of dimension of energy, and from that expression we are able to correlate the entropy function S with the energy, that is del S by del E, when a number of particles and volume are constant, that is equal to 1 by T. So del S by del E of this one, that is del of log omega E by del E, is 1 by beta T, which is a constant factor, and from this relation we obtain S is equal to K beta ln omega, which is the relation between Boltzmann's constant and entropy. Then this expression indicates that entropy is a temperature dependent function. The entropy can be changed by when temperature changes. So entropy depends on the temperature in a wide sense, and all the microstates can be possible to be accommodated within one macrostate. Then the last one is the postulate of equal a priority probability. What is the postulate? If we have thermodynamic probability omega, then we simply say the number of ways. If there are n distinguishable ways or n distinguishable objects in a cell, and n1 objects in first cell and n2 objects in second cell, then postulates of equal priority probability suggests that the number of particles in first compartment n1 can be written as 1 by a times e to the power minus beta epsilon 1, where a is a constant, that is exponential of alpha. What is alpha? What is a? A is called degeneracy parameter. When a is greater than 1, we have classical regime, that is Maxwell-Boltzmann distribution formula is obtained. This is called equal priority. Similarly, using Lagrange's multipliers, we are also capable to find the equal probability of two state of functions. Then if you go through the curve here, in Maxwell's Boltzmann distribution function, we have evaluated the Lagrangian multipliers Ni as 1 by e to the power alpha plus beta epsilon I, which is 1 by e to the power minus epsilon I minus mu divided by k beta t. The variation, this is the variation of the plot. This is called, where mu is called the chemical potential and a is called the degeneracy parameter. The distribution function varies in this manner. And you can see the beauty of this graph. It indicates that a plot of number of particles versus epsilon minus mu by k beta t indicates that the distribution function approaches zero at higher energy. And this is conformity with behavior which obtained from kinetic theory of gases. In kinetic theory of gases, we obtain this one with increase in it approaches zero when higher energy, it approaches zero at higher energy value. This leads to zero value. So it was also expected in your kinetic theory of gases. Then we have thermodynamic relations, some variables. We have discussed no thermodynamic variables: temperature, pressure, volume, and entropy. And we have defined in terms of your partition function Z, entropy S is equal to nk beta ln Z plus U by T. U is your internal energy, T is your temperature. So these relations, all these thermodynamic variables are related with entropy, as a result of which we are able to derive the Maxwell's equations, which have certain applications. In the last fourth class, we will give these from Clausius-Clapeyron equation. We will derive the phase transitions and phase transition results in Ising models. Then this principle of equal a priori probabilities indicates that what is its assumption? Now the system, if we have a system of large number of particles, then this number is fixed. That is, if bold N is total number of particles, Ni is a large number of particles of a given cell of ith cell, then sum over I Ni is equal to N, and the total energy of the system is conserved, then Ni epsilon I is equal to total energy E. So for a given thermodynamic system, there exists a set of accessible microstates. A system will not stay in a given microstate, and it continuously make the transition between various accessible microstates. This is principle of equal a priori probability. And the postulate of equal a priori probability is also called makes a postulate for equilibrium in statistical mechanics. And this hypothesis, another hypothesis known as ergodic hypothesis, which gives for a stationary system the time average of ensembles are equal and said to be ergodic. That will be discussed in a tomorrow class while dealing with this one. Let us close today. Any questions? Any questions? Okay, we left. Thank you for cooperation.